Titled From Circleometry to Trigonometry. What we're going to do is we're going to review first a little bit of special right triangles and SOHCAHTOA from geometry, and then we're going to extend that into something called the unit circle and how that plays out. So first what we're going to do is look at the opening exercise for lesson 4, and in that one we have three triangles, one with a 30 degrees, one with a 45, and one with a 60. So if you recall from geometry, there were some patterns that were involved with special right triangles. So what I'm going to do is superimpose onto this one that the side opposite the 30 degrees we are going to denote as x. The side opposite of this other degree, which I'll note that this is 30 and this is 90, then this has to be 60 degrees. Now that's important to note for later in this triangle over here that already has a 60 degrees. So with that being the case, the angle opposite of the 60 is going to be x square roots of 3. And the side that is here, which is known as the hypotenuse, which is opposite the 90-degree angle, is where we denote the portion of the triangle as 2x. Now this is a special relationship for all 30, 60, 90 triangles. So the reason why that's important is what we're going to note is we look at this part right here and we can see a little one-step equation being developed. 2x equals 1. So if I were to solve that over on the side, if I had 2x equals 1 and I solve for x, I find out that x is equal to 1/2. Now why does that matter? Because now I know that this side right here is 1/2, and then this part right here, if I plug an x into here, then I'm going to find out that AC, the side AC, is going to be equal to 1/2 square roots of 3, or you can rewrite that as the square roots of 3 over 2. So these are three important values in terms of what we are looking for in this design. If we look at the next special right triangle, this is a 45, 45, 90 triangle. So a 45, 45 degrees, 90 triangle. What does that mean? That means that this side is equal to this side. That means we have an isosceles triangle. And so that means these two sides are congruent. So this side has to be x, this side has to be x, and this is going to be x square roots of 2. Again, that's the pattern for all 45, 45, 90 triangles. So you may want to note that down somewhere, maybe in a clean triangle. And so same idea. If we're trying to solve for x, we note our one-step equation right here. And so we can go to the top where we can do some work, and we say x square roots of 2 is equal to 1. So we divide by square roots of 2. So x is equal to 1 over the square roots of 2. And whenever we taking a look and going through it, we rationalize it. So if you remember that, rationalizing, that means we multiply top and bottom by the square roots of 2. And so we end up with square roots of 2 over 2 as the result. And thusly, if that's x, then that goes there, and that one goes there. And so we're able to solve that one. This last one has a 60 is also the same as the other triangle. So this is another 30, 60, 90 triangle. Remember, opposite of the 30 is the x. We'll change that into a different color. Opposite of the 60 is the x square roots of 3. And then opposite the hypotenuse is our 2x. Now, we technically already solved this one because it's the exact same triangle as what we have over here. So we know that x is going to equal 1/2. And then over here, this is going to be the square roots of 3 over 2 after you end up finishing that particular piece. So again, these are your three special right triangles, or I should say your two special right triangles, a 30, 60, 90, and a 45, 45, 90. You want to note these because we're going to be using these values, the square roots of 3 over 2, the 1/2, the square roots of 2 over 2, over and over again in this particular lesson. The final part of review is in number 2 in the opening exercise, where it says, given the following right triangle, we have angle A, which is theta. They want us to find the sine of theta and the cosine of theta. This is just to give you a chance to recall your sine, cosine, and tangent. And so sine, as a note, is opposite over hypotenuse, and then your cosine is adjacent over hypotenuse, and the tangent, which we're not going to use today, is opposite over adjacent. And so some people reference this as SOHCAHTOA, a different way to kind of remember the order in which these go. And so if they're asking us to find the sine of theta, sine is opposite over hypotenuse. So sine of theta, opposite is 5, hypotenuse is 13, so it's 5 over 13. And if we wanted to find the cosine of theta, that would be adjacent over hypotenuse. So adjacent would be 12, and the hypotenuse would be 13. So that wraps up our review of geometry that's going to lead us into where we're going today. So when we turn the page in our book and we look at example number 1, we get our first look at what's called a unit circle. So I'm going to underline that. We're looking at an image called the unit circle. And the unit circle has a couple of characteristics to it. One thing that it has is called the initial ray, which is right here. The initial ray is the ray that's towards the bottom, and so I'll highlight that. This would be our initial ray on a unit circle. It's always the part along the x-axis. And then there's another part that we can classify called the terminal ray. The terminal ray is the ray that rotates. It moves around the circle, kind of like a spinner. If you were to spin it, and then it would land at some point on the circle. And so wherever that point is our point of interest. We call that point P, which is right there. Now, what's characteristic about the unit circle is our equation for a circle is x squared plus y squared equals 1. And the 1 is the important part, because what we want to note is that formula in its generic version says x squared plus y squared equals r squared. The r represents our radius. And so since this is a 1, the square root of 1 is just 1. Now, why do I mention that? Is that all of the radii, so all the hypotenuse that we're going to see today, is going to have a length of 1 from point O all the way to point P. This distance will always be a 1 regardless of where we are on the circle, due to how a radius works. So with that definition, right, we take a look at these. They want us to find the sine of 30 and the cosine of 30. So remember, sine, we just mentioned a minute ago, is opposite over hypotenuse, and the cosine is adjacent over hypotenuse. They want us to find first what is the length of OQ. So OQ, right, that's not the entire red line. OQ literally goes, if I highlight that, from here to here. This green line would be OQ. They want to know what is the length of that. Now again, remember, this is a 30-degree triangle. This is 90, which also means that this angle right here has to be 60. Remember that geometry that we just practiced? We could superimpose our info that opposite of 30 is x. This right here is going to be x radical 3. And this right here is equal to 2x. Now again, once you know the pattern, you don't need to do this part over and over again, because what we are going to have to understand is that if this is where x is at, then this side has to be 1/2. And this side over here is going to be the square roots of 3 over 2. And it's going to always play out whenever we're doing these particular pieces. So therefore, we could say, what is the length of OQ? Well, we could say that OQ is the length of square roots of 3 over 2. Then they ask, what is the length of QP? And so then we can say, well, the length of QP is going to be this distance right here from Q to P. And we denoted that length as 1/2. So we could say that QP is equal to 1/2. Now that allows us to find the sine of 30 and the cosine of 30. Remember, we just said the sine of 30 is opposite over hypotenuse. So the opposite of 30 degrees is 1/2, the hypotenuse is 1. So that means sine of 30 would be 1/2 divided by 1, which is simply 1/2. Now, if we did the cosine of 30, right, the cosine of 30 is adjacent over hypotenuse. So that would be the square roots of 3 over 2 divided by 1. And so that means that would be the square roots of 3 over 2. That would be the cosine of 30 degrees. And so again, I can't emphasize enough, this borrows information from the geometry, the opening exercise that we talked about with 30, 60, 90 triangles and 45, 45, 90 triangles, which is what we're going to show next in this particular piece. So when we look at exercise 1 and 2, it says suppose P is a point on the unit circle, right? So we'll add a unit circle. So we'll take it, just draw any random circle. It doesn't matter how big or small you draw it. And then we'll put an axis across here, and we'll put an axis across there. And to start to show what we have, we'll let this be our initial ray. Our terminal ray this time is going to be right here, and I'll explain that in a minute. And so here's going to be our point P. So what is our question asking? Suppose point P is on the unit circle and obtained by rotating the initial ray, so we'll just denote this as IR, initial ray, through 45 degrees. So that makes this the terminal ray. That means we open this up so that it is 45 degrees. 45 degrees. Now, why is that significant? Because now what I can do is I can draw a line straight down from here to here, and this creates my right triangle. So the part that we're interested in is this piece that we can see. So we have a 45, 45, 90 triangle. Now, if you remember from our opening exercise again, we know that this side is equal to this side, and this is going to be a 1. So if we were to solve it, we would find out that this part right here is the square roots of 2 over 2, and this one right here has to be the square roots of 2 over 2. And so that helps us answer our question. If we want to know the sine of 45 degrees, we know that is opposite over hypotenuse. And so that's the square roots of 2 over 2 divided by 1. And so we just end up with the square roots of 2 over 2. Same thing with cosine 45. Cosine 45 is adjacent over hypotenuse. So that means that's going to also be the square roots of 2 over 2 divided by 1. And our result will be the square roots of 2 over 2. We'll show this one more time. What I'm going to do is I'm going to copy this. And we're going to show this again. Let's see, paste. And we're going to take some of the writing off. And what we want to be able to do is open this up. This time our directions say to 60 degrees. So if this is my terminal ray, right? My terminal ray rotates like this. So this would be like 0 degrees. This would be about where 30 degrees is, 45 degrees, 60 degrees would be up here. So it's like a spinning wheel like we talked about earlier. And so if that's the case, right, we would take our line and we would draw it straight down right here. And so our new point P is going to be right here. And again, this is our terminal ray. This is our initial ray. And so as I fill this in, I know that this is going to be 60 degrees. This is going to be my 90. And this will therefore become my 30 degrees. Now again, leaning on the geometry at the beginning and the fact that a 30-60-90 triangle is the same thing as a 60-30 triangle, we should be able to acknowledge now very easily that this is going to be 1/2, and this is going to be the square roots of 3 over 2, and we know that this side here is 1. These are patterns that really would be recommended that you kind of memorize. That way you don't have to calculate them every single time. And so if we wanted to know the sine of 60 degrees, again, remember sine is opposite over hypotenuse. So the opposite of 60 would be the square roots of 3 over 2. The hypotenuse is 1. So therefore we get the square roots of 3 over 2. And if I want to do the cosine of 60 degrees, that would be adjacent over hypotenuse. And so that would be 1/2 over 1. And that would just give us 1/2 after that is simplified. So again, remember, just as we wrap these particular exercises up, this is what the unit circle looks like. It's an x squared plus y squared, and the radius is always equal to 1. And so that's how this plays out. Now, just for extra knowledge, right, what we found out when we did this point P right here, we'll just point to it, is the information that we just found. 1/2, comma, square roots of 3 over 2. Now, we'll elaborate on that later, but that's the actual location right here that we have found. So they ask us then in this particular example, and this is on the bottom of the page that we were on, what if we had the sine of 150 degrees? Well, let's think about what we have. We've got our initial ray, which is right here. And right now, let's just say we think about where our ray is going to be at. This would be, for example, 45 degrees. We're not interested in that one. If I were to draw a line straight up, this would be 90 degrees. Again, we're trying to think where 150 degrees would be at. If I drew a line over here, this would be a semicircle, 180 degrees. So 150 is close to 180. In fact, the only difference between 180 and 150 is about 30 degrees. So what I'm going to do is I'm going to come up approximately 30 degrees higher than 180. Now, just for references, we'll just add this. This is where 90 degrees was at. This is where 180 degrees would be at. And so this would represent 150 degrees. So what do we know about this? This is going to introduce something called a reference angle. We have only two special right triangles, a 30, 60, 90 and a 45, 45, 90. So what we're going to do is we're going to draw a line straight down right here. And then we're going to come across this way. And now I'll do an extra highlight. This is going to be our special right triangle right here. And so what I can observe and I can write is that this is going to be 30 degrees right here, because the difference between 180 and 150 is 30 degrees. This is going to be my 90 degrees. And so therefore this has to be my 60 degrees. Now that just means it's in a different location. What doesn't change is that this radius is still 1. This opposite of 30 is still known as my x, and this is going to be my x radical 3. So that means by now I know that this side right here is going to be equal to 1/2. And this side right here has to be the square roots of 3 over 2. Now, the only difference is we went to the left. So if you think about a number line, right? On a number line or on a coordinate plane, everything over here is positive, positive. Everything over here is negative, positive. Down here on a coordinate system, this would be negative, negative, and everything over here would be positive, negative. So why is that necessary? Well, that just means that this is going to be a negative square roots of 3 over 2 because we moved to the left on the number line. So if I want to know the sign, now remember, let me mention this. Right? This is important to note. This from this initial ray all the way to here is 150 degrees. Don't make a mistake about that. That opening is 150 degrees. The difference between 150 and 180 is 30. 30 degrees is called our reference angle. We're using that angle to be able to get our 1/2 and our negative square roots of 3. So if I want to know the sine of 150, right, I am going to use this green triangle that was created after opening up 150. So if I said the opposite over hypotenuse, right, so opposite over hypotenuse would again be 1/2 over 1, and so therefore the sine of 150 would also be 1/2. If I want to know the cosine of 150, that would be the adjacent over hypotenuse, and so that would be negative square roots of 3 over 2 over 1, so therefore this would be the negative square roots of 3 over 2. Right? By comparison, I'll just mention this. If I had done the sine of 30, now remember where sine of 30 is. 30 degrees would be over here. That would have created this triangle on this side, just as a quick reference. This is where 30 degrees would be at. Sine of 30 would be 1/2, just like the sine of 150. But if I actually said the cosine of 30 rather than the cosine of 150, it would be a positive square roots of 3 over 2. I mention that just so you could see the difference between the 150 version and the 30 version. The 150 version puts us in quadrant number 2, whereas the 30 version leaves us in quadrant number 1 in that perspective. So our next note at the top of the next page is just a reference piece. They want us to note, right, that if we are in this quadrant, everything, well, let's start with quadrant 1, everything over here is positive, positive. Everything over here is negative, positive. We mentioned this already. In this quadrant, everything is negative, negative. And everything over here is positive, negative. So all my sine values over here would be positive. All my cosines would be positive. Over here, my cosines would be negative, and my sines would be positive. And then that continues to work itself around as we go through. So that leaves us with just a few exercises to take a look. And they say, what if we were to do 120 degrees? So we'll do a circle. Let's not do a green circle. Green's good for highlighting. So we'll draw a y-axis, and we'll draw an x-axis. And what we'll do is we'll put our initial ray. Our initial ray is always right here. And it says they want us to open up to 120 degrees, right? So remember, 90 degrees is right here. 120 is 30 degrees more than 90. So that means my terminal ray is going to open up right there. That means that this angle right here is 120 degrees. But what I need is I need a reference angle. My reference angle is going to be the angle that is created by dropping a line straight down to the x-axis. So by doing that, I end up creating a right triangle with the x-axis. Always with the x-axis, never the y-axis here. And so the difference between 120 and 180, right? 180 minus 120 is 60 degrees. So my reference angle is 60 degrees. That makes my 30 degrees right there. Now again, you should start seeing some obvious things happening. That means this side right here is going to be 1/2. We're going to make it negative because it's on the left-hand side. This is going to be the square roots of 3 over 2. And this is always going to be a 1. So if I want to know the sine of 120 degrees, I am going to use this reference triangle because that's what was created after I opened this up 120. So from this angle, opposite over hypotenuse, and so I'm going to get the square roots of 3 over 2 over 1, and so it's going to become the square roots of 3 over 2. Remember, everything in this quadrant, right, let's emphasize that again, everything in this quadrant is negative, positive, so we would expect our sine value to be positive. Now when we do cosine, the cosine of 120, that is going to be adjacent. My adjacent is negative 1/2 over 1. And so then I'm going to get negative 1/2. In number 4, they say, what if we've got 240 degrees? Okay, so 240 degrees. So we're going to draw a new unit circle. So here's a circle. We'll put a y-axis. I'll need to center that a little bit better, I think. There's my x-axis. Let's grab this line and slide it over. That looks a little bit better. We should always include our initial ray, which is right here. And then our terminal ray is 240 degrees. So just as reference, right, let's remind ourselves, this is 90, this is 180, this is going to be 270, and this is going to be 360 degrees, which is also known as 0 degrees. We'll put our little degree symbols on each one. And so we're looking for 240 degrees, right? So when we do our terminal ray, this is 270. I know that 240 is close to 270. In fact, the only difference between the two is 30 degrees, right? So that's like me starting my wheel right here, and I rotate it around, and it keeps rotating 90 degrees, rotating 180 degrees, and I'm approaching 240 degrees. So that's roughly right there. And so what we're curious in is in finding this point P that is right there. So what I'm going to create is I need to create my reference triangle so that way I can find my reference angle. That is going to be the angle I'm going to use so I know what special right triangle to develop. So to make this work, what I will do is I will draw a line straight up to the x-axis, and where it intersects the x-axis, I'm going to come across to the center of my circle. This creates my special right triangle. Now again, remember, right? Remember, this is 240 degrees. 240 degrees goes from here all the way to there. The difference between here and here is 30 degrees. So if this part right here is 30, then this part inside of here, let me erase that so I have room to write. This space right here is going to have to be 60 degrees. And so that also makes this another 30. And so again, I see a 30, 60, 90 triangle. Now again, that's important because I know now that this side right here is going to be 1/2 with a negative, and this is going to be the square roots of 3 over 2, but this time it's going to have a negative because we're going down. And of course this is going to be our 1, because remember everything here is going to be negative, negative. So my reference angle, we said, is going to be 60 degrees. That's how we were able to use the negative 1/2 and the negative square roots of 3. So if I want to find the sine of 240, I set that equal. Remember, that is opposite over hypotenuse. We'll emphasize that. We haven't written that in a couple of slides. So the opposite of 60 degrees is going to be the negative square roots of 3 over 2. The hypotenuse is 1. And so we're going to get the negative square roots of 3 over 2. And then the cosine of 240 is the adjacent over the hypotenuse. And so it's going to be negative 1/2 over 1. And so we get negative 1/2. We have one more exercise, exercise number 5. It's at the top of the last page of this section for the notes. And this one's going to take us into the fourth quadrant. So we'll make one more circle, right? It is recommended, even though the directions do not say to draw a circle, it is recommended each time to draw a little circle. I like to call these little helper circles. The unit circle. A visual helps understand where things need to go. So we'll put our initial ray here. And then for our terminal ray, we're going to try to get to 330 degrees. So, right, this is 0 degrees. This would be 45. This would be 90. We'll skip all the way to 180. We'll go all the way down to 270. And 330 is very close to 360. 360 is all the way around the circle. So if I go backwards 30 degrees a little bit, this would be 330 degrees. So now that I have 330 found, what I'm going to do is we're going to draw a line straight up, right there, and then we're going to go across, and then we would go back this way. This would create our special right triangle. And so this reference angle this time would be 30. This is where 60 would be at, and this would be 90. Right? Remember, we opened this up to 330 degrees. This is where 360 would be at. This is where 330 is marked at. So with that being the case, if this is 30 degrees in the middle, that means this has to be 1/2. We'll mark it as negative because we went down. And then this is going to be the square roots of 3 over 2. And our hypotenuse is always 1. So just a note, right, our reference angle, is 30 degrees because we're 30 degrees away from the x-axis. So if I want to know the sine of 330 degrees, then that's going to be the opposite over the hypotenuse. And so that's going to be negative 1/2 over 1. And then therefore we end up with negative 1/2. If I do the cosine of 330, then that's going to be adjacent over hypotenuse. And so it's going to be the square roots of 3 over 2 divided by 1. And so then I get the square roots of 3 over 2. The last thing you're going to find in this section is a complete unit circle. Wrong one. This is the one that's in your book. And so this is kind of like a cheat sheet. You can use this for your problem set and your homework. And rather than having to draw the triangles every single time, what this does is a whole reference sheet. This would be a 30-degree triangle. So this right here would be your cosine of 30, and this right here would be your sine of 30. If I went to the next one, right here, 45, that means this square roots of 2 over 2 would be your cosine of 45. And this one right here would be your sine of 45. Likewise, if I looked right here, this one right here would be my cosine of 60, and this one right here would be my sine of 60. And they give you the references all the way around: 120, 135, 150, 180, 210, 225, 240, right? And so this is just a cheat sheet. This is not a magical piece, but you're welcome to use this rather than having to draw the triangles every single time. So that would conclude this lesson. And this should move you into the problem set to see how well you understand the content.